lecture, we have discussed the concept of aromaticity and anti-aromaticity and the various structural features which are needed to be present in a compound to be an aromatic compound, and also we discussed the nomenclature of benzene compounds. In today's presentation, we will discuss electrophilic substitution reactions of benzene, and in this we discuss the mechanism, how the reaction proceed, the evidence of the mechanism and the various electrophilic substitution reactions like nitration, halogenation, sulfonation, Friedel-Crafts alkylation and Friedel-Crafts acylation. So, we know all aromatic compounds undergo electrophilic aromatic substitution reactions. In last lecture, we have seen this also. Here now you can see this is a benzene ring and this is an electrophile. So, if we react this electrophile, substitute one of the hydrogen from the benzene ring to give the substituted product. Now, what is the difference? Like alkene, benzene is also having a pi electron density above and below the plane of the ring. So, benzene reacts like a nucleophile, but major difference between alkene and benzene is that in benzene pi electrons are not localized, these are delocalized and these form a stable aromatic system. Now, we look again into the reaction. Benzene acts as a nucleophile and it attacks this electrophile and gives the intermediate carbocation. Now, this carbocation is getting stabilized via resonance and produces a resonance hybrid, this one, and which is known as the sigma complex. Why sigma complex? Because there is a new sigma bond formed of the ring with the electrophile, but this is not aromatic in nature. Sigma bond interrupts between this delocalization of 6 carbon. These 5 carbons are sp2 hybridized, but now this becomes sp3 hybridized carbon. Further studies also suggest that before formation of this sigma complex, there is a formation of a pi complex. See here, this electrophile and this benzene rings, this comes together and there is a formation, because this is a electron rich, this is a electron deficient. So, there is a interaction between these two moieties. So, first this electrostatic attraction is there between the two reactants and this is known as a pi complex, and there is no formation of bond here, it is just the attraction between two reactants, and then this electrophile forms a bond and convert into a sigma complex. So, we know now from this it is clear there is a first formation of pi complex, but pi complex is not as stable as sigma complex because it is just an interaction and there is no bond formation and it is of high energy as compared to sigma complex. As I told you before also, formation of this sigma complex, this is endothermic in nature, this step, and because there is a loss of aromaticity. Now, the next step, this sigma complex loses this H plus ion and to give a stable substituted benzene ring, and we get back our aromatic system back. So, this is a fast step and this is a exothermic in nature because here we get back the stable system back. This is very much clear in the energy profile diagram. These are the two reactants. When these come close to each other, kinetic energy changes into potential energy and this reaches this height and this then convert into a this sigma complex. There is a formation of this carbocation intermediate and then this carbocation readily loses this H plus and gives you the substituted product which is a stable one. So, this is a two-step reaction. Now, next, how can we say this is a two-step reaction? It can be a one-step reaction also. Now, see, in two-step reaction as we discussed, there is an attack of electrophile to give an intermediate benzenonium ion or sigma complex, and then this sigma complex react with a base to give the H plus, and this substituted product we get. But if we see, this reaction can also takes place in one step. This nucleophile can attack, here there is a simultaneous formation of the bond with electrophile and simultaneous breaking of this H plus from the benzene ring to give this intermediate transition state, and then there is a complete bond breaking and complete bond formation and gives the substituted product. Now, to prove whether the mechanism is two step or a one step, we take the isotope effect. A variety of aromatic compounds labeled with deuterium or tritium were subjected to nitration, bromination and Friedel-Crafts alkylation, that is various electrophilic substitution reactions, and it was observed that deuterium or tritium isotope of proton H plus is replaced at the same rate as protium, means there is no significant isotope effect. So, what this indicate that? Now, we know that carbon and deuterium bond break slowly as compared to carbon and protium bond, and if this carbon hydrogen bond breaking takes place in rate determining step, then this rate should be high for carbon and deuterium compound when there is a replacement of proton from the deuterium. So, but what we observe, the reaction rate is same. So, this indicates that there is no involvement of breaking of a carbon hydrogen bond in rate determining step, and this interpretation is inconsistent with the two step mechanism. That is, first step involves the slow attachment of an electrophile to the aromatic ring to form a intermediate carbocation. Then in second step, first form the carbocation readily loses hydrogen ion to form the product, and since first step is the slow one, so that is why the first step is the rate determining step and which do not involve breaking of carbon hydrogen bond. So, that is why the overall reaction is independent of the isotope effect. Now, we come to the different electrophilic substitution reactions. First one we discuss nitration. In nitration, benzene react with the nitrating mixture which consists of two acids, concentrated nitric acid and concentrated sulfuric acid. This on heating gives the product nitrobenzene. So, this is a electrophilic substitution reaction. So, we should understand from where the electrophile comes. So, that we can understand by taking the mechanism. So, mechanism involves different steps. The first step is generation of electrophile. Here the electrophile is generated with the help of concentrated nitric acid and sulfuric acid. These two acids reacts and produces a electrophile nitronium ion. This nitronium ion form, how this nitronium ion get formed? These are two acids. So, how these react? This is a type of Lowry-Bronsted acid base reaction. Here the nitric acid act as a base and this sulfuric acid act as a acid. So, it supplies H plus to the nitric acid and there is a protonation of this OH. Now, next there is a removal of this water from this molecule and produces a nitronium ion which is a very good electrophile. Now, this electrophile then react with benzene system, again produces an intermediate benzenonium ion and which gets stabilized via delocalization of this positive charge and produces a sigma complex. So, again this is a first step and it is a slow step. So, there is a slow attack of this electrophile on benzene, and in second step which is a fast step, there is a removal of this H plus with the help of this base HSO4 minus and produces nitrobenzene and sulfuric acid. Now, this is a energy profile diagram of nitration. So, these are the starting material, benzene, nitric and sulfuric acid. So, there is a rise in potential energy, and when this reach a transition state, this gives the intermediate. There is a valley, this is corresponding to this stabilized carbocation, which is a sigma complex, and then there is again for the second step, again there is a breaking of this carbon hydrogen bond. This reaches this transition state first and then gives the product, that is a substituted one. Now, next reaction is halogenation. Halogenation, we can have a chlorination. For chlorination, benzene react with chlorine in presence of a Lewis acid ferric chloride and gives the chlorobenzene and HCl. For bromination also, this benzene react with bromine in presence of a Lewis acid ferric bromide to gives the bromobenzene and HBr. And for iodination, it reacts because iodine is very less reactive, so it needs the assistance of a oxidizing agent nitric acid to gives the iodobenzene, but this reaction is very slow. Now, here in chlorination and bromination, as we have seen, there is a need of Lewis acid, ferric chloride and ferric bromide. As we discussed in our first lecture, the chlorination and bromination of alkene, the reaction of chlorine and bromine with alkene, there we discussed it, chlorine and bromine only react in CCl4. There is no need of any Lewis acid there, because there is a major difference between the reactivity of alkene and benzene. As we discussed earlier also, in alkene there is a localized double bond. So, that double bond creates a polarity in the bromine molecule, and through this bromine supplies electrophile to the alkene system. But here, due to the delocalization of pi electrons, benzene is not able to develop a polarization in this chlorine and bromine molecule. So, that is why here for generation of a electrophile there need a assistance of Lewis acid. So, now next we see how this reaction proceed. So, bromination of benzene. So, first step is again generation of an electrophile. So, bromine molecule, this reacts with ferric bromide and produces this complex. Now, see this complex, bromine which is having a positive charge, there is a polarity created here, and this supplies this bromine as Br plus when benzene attacks. Now, see in how this benzene attacks, this is a nucleophile, this attacks this bromine and there is a breaking of this bond and there is a removal of FeBr4 minus and formation of this intermediate benzenonium ion. Again this benzenonium ion will get stabilized via delocalization of positive charge and gives the stabilized sigma complex. Now, the next step is removal of this H plus with the help of base. Base is FeBr4 minus. So, now you see how this is removed. This Br takes this H plus and these electrons shift to the benzene ring and we get the bromobenzene and HBr and our Lewis acid back, that is ferric bromide. For iodination, the nitric acid here, it helps in generation of a electrophile I plus, and as I told you before, this reaction is very slow. So, for iodination of benzene there are many other good methods for a reaction. Now, this is the energy profile diagram, it is the same. First these two benzene ring and this halonium ion reacts to give the intermediate carbocation and then this intermediate carbocation gives the substituted benzene ring. Now, the next reaction is sulfonation. Sulfonation means what? Benzene on reaction with sulfuric acid gives benzene sulfonic acid. But here the next question is, what is the electrophile here? The electrophile is sulfur trioxide, which can be generated from by heating concentrated sulfuric acid. So, we need a heating of this concentrated sulfuric acid which produces sulfur trioxide. So, that is why reaction is slow with concentrated sulfuric acid. But if we take fuming sulfuric acid is a mixture of concentrated sulfuric acid and sulfur trioxide, and that is having a high concentration of sulfur trioxide. So, it can be a good source of our electrophile. So, that is why reaction is fast with fuming sulfuric acid. Now, you see here sulfur is electron deficient. So, benzene can attack this sulfur and gives the intermediate this carbocation, and again this is a slow step. So, the next step is aromatization, that is a removal of H plus with the help of a base HSO4 minus, and it gives H2SO4 and this benzene sulfonate ion. This benzene sulfonate ion then take a proton and it gives the benzene sulfonic acid. In some cases, it was observed that the electrophile may be HSO3 plus, or there may be any molecule which can supply SO3 or HSO3 plus to the aromatic ring. And as we have seen in the reaction, all the steps here in sulfonation are reversible, and that we can easily observe in energy profile diagram also. It was observed that this reaction gives a slight isotope effect. See, if this is a, because this isotope effect will come only in the second step, because that involves the breaking of carbon hydrogen bond. If we replace this hydrogen by deuterium, then there is a slight high in the energy here, and this becomes more as compared to this, and this step becomes the slow one, and that is why it show the with the different isotope the reaction rate differ, and that is why this reaction shows the isotope effect. So, this is clear here. There is a formation of this intermediate carbocation. So, now here both the forward reaction and backward reaction, the rates are almost same. If we take dilute sulfuric acid, we get back our benzene ring. If we take concentrated sulfuric acid, then we get the product our benzene sulfonic acid. Next example of electrophilic substitution reaction is Friedel-Crafts alkylation and acylation. This reaction was given by two scientists, Friedel and Crafts, and that is why known as Friedel-Crafts alkylation and acylation. In this reaction, benzene reacts with alkyl halide in presence of a Lewis acid to gives the alkyl benzene and HCl. Now, here again the role of Lewis acid is in production of a electrophile, that is this alkyl carbocation, and how this is produced. This alkyl halide reacts with this aluminum chloride and forms this intermediate charge complex and carbon Cl bond. This becomes polar in nature, and this get break and gives the free carbocation and a base AlCl4 minus. Now, this carbocation, because this is a electrophile, it is a electron deficient species, this one is attacked by this benzene ring, and again there is a formation of an intermediate carbocation, and this is a slow step. And now, next step, the second step is aromatization, that is removal of this H plus with the help of a base AlCl4 minus. So, here Cl, this bond get break. So, this Cl takes this H plus and produces HCl and aluminum chloride we get back and alkyl benzene. Now, in certain cases there may be possible there is no free generation of the carbocation. So, this charge complex directly can attack by the benzene ring. So, benzene ring takes this R group from this complex and we get the intermediate carbocation. So, this reaction we will discuss later on also. when we will discuss the alkyl benzenes. Now, carbocation cannot be only produced by alkyl halide by reaction with Lewis acid. The carbocation can be generated in other ways also. For example, we can react alkene with a acid and there is a formation, for example, this is propene which on reaction with HF and produces the isopropyl carbocation, and this isopropyl carbocation as the normal course attacked by the benzene ring and gives the isopropyl benzene. So, here instead of alkyl halide we have used this alkene propene. Now, for formation of carbocation we can also use alcohol. So, alcohol in presence of a Lewis acid or protonic acid can also be used and it can also produce the alkyl benzene, because here again R plus the carbocation can be formed. Now, Friedel-Crafts acylation. Here instead of alkyl halide we take the acyl halide, like benzene on reaction with acyl chloride again in presence of a Lewis acid on heating and forms the acyl benzene, or we can say aryl alkyl ketone. Example is on reaction with acetyl chloride in presence of aluminium chloride, it produces a acetophenone, aromatic ketone. Again the role of Lewis acid is same, aluminium chloride, it helps in production of this carbocation which is known here is acylium ion. So, how this is produced? This acyl chloride, this chlorine is having a lone pair of electrons. So, this attack this Lewis acid and forms the intermediate complex. Now, this intermediate complex, this bond becomes weak and this bond get break and produces this intermediate cation, and this cation is resonance stabilized and which is known as the acylium ion and ACl4 minus as a base. Now, this acylium ion is attacked by this benzene ring and produces this intermediate carbocation, and this intermediate carbocation then loses this H plus with the help of a base and produces this ketone or acyl benzene. Now, today we have discussed the reactions, electrophilic substitution reactions of benzene, and we have seen this reaction takes place in two steps. In first step, the electrophile attacks the benzene ring and which is a slow step and rate determining step, and second step is the removal of H plus to give back the aromatic system, and that is a fast step because once the carbocation forms it readily loses H plus to the base and gives the substituted product. And we have seen the isotope effect to prove our mechanism also, and then we discuss different examples of electrophilic substitution reactions. First one was nitration, in which the electrophile was nitronium ion which was generated with the help of a mixed acid, nitric acid and sulfuric acid, and then we have seen how this nitronium ion attacks the benzene ring. In second reaction, halogenation, we have seen chlorination and bromination. Generation of electrophile needs the help of a Lewis acid, ferric chloride in the case of chlorination and ferric bromide in case of bromination, and there is a formation of an intermediate complex which supplies electrophile to the benzene ring. And then we have seen sulfonation, there is a neutral molecule sulfur trioxide act as a electrophile and which can be supplied by concentrated sulfuric acid or fuming sulfuric acid, and fuming sulfuric acid is a better reagent because that have a rich source of sulfur trioxide, and we have seen also sulfonation is a reversible reaction and that shows a slight isotope effect also, and that is why we can vary by varying the reaction conditions we can do desulfonation also. If we take concentrated sulfuric acid we get the benzene sulfonic acid, and if we take a water or we do the reaction in presence of a steam then we get the desulfonation and we can remove easily sulfonic acid group from the benzene ring. And then we discussed the Friedel-Crafts alkylation and acylation reactions, and these are very important because this brings the alkyl group to the benzene ring or acyl group to the benzene ring, and this we can, for alkylation we can use different reagents which can produce a carbocation like we discussed today. We use alkyl halide in presence of a Lewis acid, we can take alkene in presence of a acid, we can take even alcohol in presence of a Lewis acid or a normal protonic acid. So, we can take different conditions in which we can produce a carbocation which is a electrophile in case of Friedel-Crafts alkylation. This reaction we will discuss further in alkyl benzene in later lectures also, and in and then we discuss the Friedel-Crafts acylation, and where we discuss the for acyl group can we bring by a reaction with acyl halides. An example is acetyl chloride, and this acyl group can also be bring by reaction with acetic anhydride also. Acetic anhydride also can supply acyl group to the benzene ring. So, all these reactions we have seen today and their mechanism. So, in the next lecture we will discuss the Friedel-Crafts reaction in detail, the limitation of, there are certain limitations also of these reactions, and the alkyl benzene. How this alkyl benzene get formed, different methods as we have seen today. There is one method is your Friedel-Crafts and other methods also, and their reactions. How, because there in alkyl benzene we have a side chain alkyl group. So, how this side chain behaves when this is present along with the benzene ring. So, all these things we will discuss in the next lecture. Thank you.